Okay, so once again, I was looking at Reddit Homework Help, and I found this really nice problem about conservation of momentum. And well, in the solution, there is attached solution to the problem, but in my opinion, solution is way too vague. It's nowhere near precise as it should be. Also, the angles in the images are a bit weird. So they let the user who made the post, they let him to make a mistake. So I guess the problem was set up to catch you off guard. And yeah, let's get into it. So the problem states, if coin A collides with coin B at an angle, both coins move off in different directions. So this is before the collision. Coin A was moving, coin B was relatively stationary. After the collision, what we have is coin B flying off towards up and right, and coin A flying off, of course, downwards and right. And the question has two parts. First part says show that the velocity of coin A immediately after the collision is about 3 centimeters or centimeters per second. And then the second part asks determine the initial velocity of the coin just before the collision. We of course assume no friction. At least there wasn't any talk about the friction in the question, so we assume there isn't any. And yeah, about the weird angles, I will attach the image of the question over it because I am not sure if I'll be able to draw this well enough. But more or less, this is the scheme, the graph, and then we have that the angle from the coin B to the y-axis, which is such a weird angle to give, is 40 degrees, and the angle from the negative part of the y-axis, which is even weirder, I guess, is the right way to say it, weirder to write, is 55 degrees. So immediately with these angles, we should forget about them because they are not really the angles that we should ever be looking at. Of course we can, and of course it can work, but as we know from basic calculus analysis courses or whatever courses you had, if we had the unit sphere, we mostly always start from here, from the positive part of the x-axis. In later courses of especially like convex and complex analysis, you kind of get a sense why we start from here. And yeah, so we should try to keep always starting from the positive part of the x-axis. Of course, there are some problems where you don't, but more often than not, this is just 50 degrees and this is just 35 degrees. And there, I think if this was stated like this in the problem, I think the original poster wouldn't make a mistake. Now, let's start. So, oh yeah, by the way, there is one more information. That's the velocity after impact of B is 2.2 centimeters per second, which is also a weird measurement, but okay, coins, I guess. So let's start solving. First question asks us what the value of the coin A, I guess we could use it like this, where t is bigger than some t0, which is time of impact. But that could also confuse you, because right now they're not requiring us any formulas or whatnot, any time relation. So we can just write VA after impact, and then they also ask us about VA, but now before impact. Really simple, nice problem, but the way the graphs are drawn in the original problem is just a no. So what do we know? Well, first of all, we know that we are working in 2 dimensions. Let's draw them like this. This is x-axis, this is y-axis. So immediately when you work in 2 dimensions, try it's not related to how young you are. You should try as soon as you understand anything about vectors. You should really try to use them, especially when it comes to velocity. So if I have a point, any point, and if this is its velocity, okay, we can always do what this problem kind of made you do, and say, okay, well, this is now the velocity in the x-axis. I apologize. Now this is the velocity in the x-axis, and this is the velocity in the y-axis. But we could just easily say, well, this is the velocity, and let's name this dot A. Well, then this is velocity A. And what's velocity A? Well, that's a vector, velocity AX, velocity AY. And now you've put 2 variables into 1 vector. Why is this good? Well, just based on the sign of these variables, we immediately know towards where the velocity vector is pointing. So if they're both positive, it will point towards the first quadrant. And if one of them is 0, then, for example, if this is 0, then it will just be parallel to x-axis. If this is 0, then it will be parallel to y-axis. And if one of them is negative, let's say VAX, but the other one is positive, then it will go like backwards and up. So yeah, it's it makes mistakes much more difficult to make. Of course, you can always make mistakes, that's normal. Everyone makes mistakes. But please, if you understand vectors, this shouldn't really be that difficult. Please start using them, okay? Let's not worry if the problem is only in 1 dimension, if the part of the problem that we are looking at is only 1 direction. If the entire problem is in 2 dimensions, we should look at vectors. If it's in 3, we should look also at vectors, sometimes in matrices and whatnot. But anything that's larger than 1 dimension, just vectors. So for the first part of the problem, well, we have what we do know is that the MV is constant. This is just the momentum, conservation momentum. It has to be constant, of course, when we are looking at the same point. I mean, if you're looking at the different points, then it doesn't make sense. But what we also know is that upon impact, so before impact, what do we have? Let's write still within this system. So we have A going horizontally, moving with velocity VA. I will just say 0 because the velocity at which it was moving was constant. And this is a vector. You can write it like this or like this. I will prefer it like this. And then B, the velocity of B was 0. Okay? So let's write this for before impact. Well, pretty simple. M times VA0, still a vector, very important, plus M, oh, by the way, it doesn't say it in the question, but I read it in the comments, masses of A and B are the same. So MA is MB, which is equal to M, and very soon we'll get rid of those masses. Well, this is M times velocity of B, which is 0. So this entire part is 0. Meaning on the left side, we only have M times the initial velocity of the coin A. Now let's look to the after. What do we have now? We have that B is moving at some velocity VB, which is a vector, and that A is moving at some velocity VA. We don't have to write the angles here. We have them in the original problem. We also have them here in our first graph. They're just there to show the, well, yeah, how steep is the velocity compared to the x-axis. Let's just write this for the after case. Well, really simple. VA plus, I'm sorry, I had to pause the recording. So I kind of lost contact. Let's see, where were we? Oh yeah, so this is just mass times velocity of B. These two are vectors as well. And now for the first question, we are asked, or for the first part of the question, we are asked about the velocity of A immediately after impact. That should be this. What can we do to get that? Well, from this, we know that vector V in our system will be Vx and Vy. It will be a vector of two components. So what do? We multiply this by Ex and by Ey. What are Ex and Ey? They are basis vectors for our coordinate system. So this would be Ex, this would be Ey. You can also write them like this, or I guess that is how you write them. Ex will be a vector 1, 0, and Ey will be vector 0, 1. Together, two of them, you can make the entire space from them. They're also the basis of the space. So what do we get? We get two equations. One equation M VA0x equals MVAX plus MVBX. Then the second one, MVA0y, MVAY, MVBY. We get these two equations. They were hidden inside of this vector equation. What do we know? We know that this is 0. And we also know the relationships between the VAY, VAX and the absolute value of the vector VA. And we also know we don't know the VA0. We can name these two angles. This is theta. Theta is, we can name these two angles. This is phi. Phi is 50 degrees. Let's name it phi B. And let's name this phi A, which will be minus 35 degrees. Why minus? Well, because it's pointing downwards. So it's either minus 35 or the 360 degrees minus the 35. But it cannot be plus 35. Plus 35 would mean that it goes up from the positive x-axis. So let's sketch the vector VB over the VBX and VBY. So we just decomposed this angle here, phi B. what do we know? Well, we know that value of VB is 2.2 centimeters per second. We know that now VBY will be just a sinus VB times the value of VB, and we know that VBX is cosinus VB times value of VB. Meaning, all of this we know. By the way, now that we have the masses, we can just divide by masses and they will disappear. So yeah, this we know. What we do not know is this. However, let's look at the equation number 2. Let's rewrite it. 0 equals VAY plus VBY, meaning that VAY will be equal to 0 minus, or we don't have to write the 0 of course, minus VBY. And what is minus VBY? Well, minus VBY is just minus of this, so minus sinus VB times the absolute value of VB. And now, since we are asked about the value VA, let's also write that down. Well, this here is going to be VA, remember negative. This will be VA vector. And these are the components, or the component vectors, I should say. VAX, VAY. The difference between the component and component vector is that the component is a number and component vector is a number multiplied by one of these two vectors. But when you draw them, they have to be vectors. So, what do we know? Let's take a look at this VAY for a second. We know that VA, the value of VA, times sine of VA will give us the VAY. We have VAY here, we have VAY here, we have VAY here. So let's plug this in. I'll just steal it. Now we can divide by this sine. And we get the value of VA. When you plug that in, minus 2.938 and so on. But we really only care about first decimal. Centimeters or seconds. Minus give plus. So we got that our velocity A is positive 2.9, but that is the magnitude of the vector. It has to be positive. That does not give us any information about the direction the vector is going towards. But what it does give us is it does give the value at the speed or velocity that the coin A will be moving. So this is what the question asked for. But the solution said this. which can be very, very, very confusing, since in a sense V is still a vector. They were somehow looking at the one-dimensional case, even though it's a 2D, and I guess they are kind of writing velocities a bit for the vector and a bit for the intensity and whatnot. But here, please, let's just write it how it should be. It should be magnitude of the vector VA after the impact. So this is after impact. And it will be 2.9 centimeters per second. Okay, so now that we have this, let's try to get the initial velocity of coin A before the collision. So what we are looking at is the magnitude of the vector VA0 before the so that's the velocity. Let's get back here. That is this velocity, this here, before the impact. Now, how can we find that? Well, we know that this is just equal to VAX. Now, VAX is a component, so we can write it like this. Why? Well, because it was moving towards the x-axis, so the y component will be 0. So what we are really looking for is VAX. Let's get back to our two equations. We can immediately see that we have it here. Now, we have this already calculated. This we can find, so it should just be as easy as plugging in. So our VAX will be, let me just take it like this. Oh, come on. VX, VAB. Amazing. Let's look at over here. VA, VX, VA. VA we know the magnitude of. So VAX, written as a component, not as a vector, will be cosine, yes, cosine of VA times the velocity of VA. Now this is all after impact, okay? So let's just quickly steal this from here. Bloop. Plus VBX. Where do we have VBX? Here. Amazing. Let's just steal it. Of course, when you're doing on paper, you can't really steal. But when you're doing it on tablet, it is a really nice function. And yeah, there it is. This is the VAX. What do we have to do? We have to plug in 2.2 here, phi b cosines of 55 degrees. VA we just calculated. This is the absolute version, so it will be 2.9. And this is where the mistake was made. Because here we're looking at the absolute value of the VA. Why? Well, let's just, this is the entire reason why I'm making this video. Let's just look at it like this. Coin A was moving horizontally. Coin B wasn't moving, so we don't need to look at it. Coin B flew up and right, and coin A flew down and right, but they're still moving right. So if we look at this like this, this will be VAX, VBX. We get this equation. This is VA0 x. So we get this equation right here, that the vector VAX must be equal to the vector VA0x, sorry, must be equal to the vector VAX plus the vector VBX. Meaning that we must sum these two vectors, or the values of these two vectors. They are both positive, even though the velocity of one of them is moving down and one of them is moving up. Their components in the direction of x are positive, and this is where the mistake was made. Because the original poster found that his velocity for the first question was negative 2.9, which to a point makes sense because we were looking really only at the vertical movement, and the vertical movement, the vertical component of the coin A will really be negative, but not the value of the vector of velocity A itself. The value of velocity A is positive. So yeah, we really have to take care when we look at directions, vector components, and vector component vectors, as well as just the vectors. We have really to think, what are we summing up? What goes in the same direction? What goes in the opposite direction? We of course know, I assume even the original poster knows, if we have two vectors going along the direction and we want to calculate the total, well, this will be, if this is A, if this is B, this will be A plus B. But let's look now at this case. So when they are going the opposite direction, if we write it like this, A and B as values, this will be A minus B. But if we just do this, if we just write, if we just write them as vectors, it still stays the same. Why? Well, because now B is already has a negative value inside of it. So yeah, that's why vectors are really cool. They will do the job for you. They really are amazing. No matter how this B looks, if we want to calculate this vector from here to here, or, well, that's a really bad example. If vector B starts here and we want to calculate this value, it will always be A plus B. Why? We start at A to 2, now we are ending at the end of B. So A plus B goes from the beginning of A to the end of B. Really easy. If they're going whatever directions they're going in, as long as beginning of one is at the end of the other, with the sum, we will get their the total vector, however you want to call it. So let me just delete this. After plugging this, all of this in, of course this is negative 35, but now here is a cosine. Cosine doesn't care for negatives, so we can just write 35, but I'll write negative 35. And let's see what do we get. Oh my, I made a mistake. This should be 50 degrees, I apologize. See, it's really easy to make mistakes. But this way at least we have a final formula, so in the end, when we plug it in, even if we make a mistake, we did most of the task correct. So always come to a formula and then plug your values in. So now with the correct angle, we get 3.79 centimeters per second. And there we go, that's the solution. This and yeah, this. So after impact 2.9, before impact 3.79. That makes sense. If we would have gotten here 1.89, I would have immediately guessed that that's an error. Why? Well, because then it would say that our velocity before oh, it should be a 0, I apologize. Velocity before impact would be smaller than velocity after impact, which doesn't make sense. So our velocity before impact 3.79 centimeters per second, our velocity after impact 2.9 centimeters per second. Thank you so much for watching. This has been a bit of a longer one than I wanted it to be. If you have any other questions, feel free to ask me. I am mostly available in the Discord. The link is in the description. I still think it's unclickable for at least a while, but you can just copy paste it. And yeah, see you next time.